Hi, this is lesson 10 in the use of JASP. And today we're going to do a few things. We're going to learn how to read in a new data set, do some basic documentation of that, do a t-test, and look again at our assumptions underlying that t-test. We're going to look at both the normality assumption and the homogeneity of variance assumption. So we'll start off by showing you how to read in a data set that isn't in the JASP library. So we're going to go to our three bars for the menu there. We're going to go to open and we're going to look on the computer and I'm going to browse and I'm already located within my desktop, some JASP videos for data for videos, and I'm going to open up this one called Bank Rev 05. Now let me show you that if I just go over to the data set and open it up in Excel, it's actually saved as a CSV file. So it automatically wants to change things into Excel. But the way that this is organized is I have the first row giving me my variable names. This is data from a bank data set that came with a old version of SPSS. I don't know if it was based in any reality or just made up. It has employee IDs, the gender of the individuals coded as simply zeros and ones. We'll talk more about that later. Education level, which is the years of education. Previous work experience, so we're going to view that as previous months of work experience. Job category, whether or not they're white or non-white, a combination of gender and minority status, which I really don't use. Their beginning salary, their current salary, how much time they've been on their current job, and their age. And so you basically have the data located under that, and there's 475 lines of data. And JASP does a very good job of picking that up, as you noticed. Let me get back out of that, go back over to JASP. And when I read in that CSV data set organized that way, it automatically picked up on the variable names in the first row. That's what it expected. Put those in as the names of my variables and then read in the data. So easy peasy, it did that as a great job. It also took a stab at figuring out what variables were what type. And I think it did a pretty good job, but I'm going to go ahead and treat education level. Here it has it as an ordinal variable. I'm going to go ahead and switch that from ordinal to scale since it's years of education that could be viewed as a true numerical scale. When I make that change over there, you'll notice that when I try and delete over here, it says, do you want to apply those changes? So I say apply, and now it's listed as a scale variable. Let's go over to sex. And when I double click on that, I'm going to leave that as a nominal variable, but I want to go ahead and code my data. This I got out of SPSS. Here's my SPSS version of that. And here it says that males were coded as 0, females were coded as 1. And so I'm going to go ahead and change this label over here to males and females. And then when I go ahead and try to close, apply, and now it nicely gives me whether it's males or females, also specifies the number. And I really like using the numbers as the basis of my data. It allows me to use it in a host of situations where I can't just use the labels. Okay, another one that we want to do is minority status. So I go over here and look at my minority classification. I notice that it was coded as 0 for white, 1 for non-white. So I'm going to go ahead and do that. Double click, 0. I'm going to put in white and 1 for non-white. And then click, apply, and now that's showing up in a useful way. One more that I want to get while I'm over here is job category. So job category, it has 7 job categories. And let's go ahead and take a look at what those are. So if I go over here to employment category, I have 7 categories. And let's see if I can arrange this so I can fill this in. There we go. So borrowing from there, 1 is clerical workers in the bank. So like your bank tellers. And there's a lot of clerical workers in a bank. So this is, I believe, the most common job in the bank. There are investment sales trainees. There are security officers. There's people in accounting, accountants, and also others who are in accounting, and customer service and sales. Technical experts. And management. Apply, and I have my changes made. Okay, let's go ahead and do a t-test. So I'm going to go ahead and do an independent groups t-test. I'm going to compare males and females in terms of the salary that they began with. So for my dependent variable, I'm going to go ahead and put in salary beginning, SALBEG for beginning salary. And here it already tells me that I have a significant test. I'm going to go ahead and ask for the location parameter, which is how big of a difference. So it's basically saying there's an $8,558 difference between those. You can tell that easier by looking at the descriptives. Here's my descriptives showing that the males entered making $24,000 on average. Females entered making $15,000 on average. Look at my effect size, getting the Cohen's d, and this is a strong effect. And I can go ahead and take a look at this using my rain cloud plots. And the rain cloud plots show that there's, the males or salaries are very highly spread out. The females are much more clustered. You can see this with the box plot, that the males, 50% of their scores are within this range, but 50% of the scores are in a very tight squeeze in range for the females. If you look at that in comparison to standard deviations, you notice that the standard deviations for the males is around 10,000, 11,000. For the females, it's around 3.6 thousand. And so, that's a big difference between the standard deviations. Yeah, you can see that a little bit in these plots over here, but the fact that the green is kind of stretched out, but it's most obvious right here, just the basic data plots that show that so spread out, and this is very clustered. Okay, did we have a normal distribution? I'm going to click on normality and QQ plot for residuals like we looked at last time. My test for the normality distribution is highly significant, and the QQ plot shows a pretty big deviation from normality. If I look at the equality of variances, that is showing that the variances are unequal. The way to view what's being compared here with this F-test is it's comparing essentially these standard deviations. Are these standard deviations equal or are they unequal? And it's basically saying those standard deviations are very unequal. Your t-test up here, your fundamental t-test, is saying, are these means equal or unequal? The 24,000 as the average that the males make versus the $15,779 that the females make. And this is saying, nope, that's a big difference of 8,558, and it's not significant. The problem is that we violated both of our assumptions. We violated both the normality assumption, as shown here with our QQ plot. We have violated the homogeneity variance assumption, as shown with this test, the Brown fourth site. There's also what's called the Levine's test. The Levine's is what shows up in SPSS automatically. And it too is showing a very significant difference. So both of those two tests are showing significant differences. The way to think about what it's showing you there is the homogeneity variance test basically argues that for two groups, the amount of variability that you have, the spread in the scores, should be equal. So if you were showing this distribution for males, you would want the same distribution for females, even if it was located in a different spot. What we see is that the distribution for males is highly spread out. The distribution for females is highly clustered. It's located in a different spot. In fact, for the females, it's located lower. But the problem is that if they're truly at the population level located in the same place, then it's possible that the test will give you faulty information. It does this most if the ends are highly unequal. So if you had 20 people here for this distribution and only 5 people here for this distribution, then it could give you wildly inaccurate results. What do you do about that? You can click on this button for the Welch test, and if you notice, if I hold over the Welch test, it says the Welch's unequal variance test. Use when the group variances cannot be assumed to be equal. Well, we have this test showing that they're not equal, so you can use the Welch test. You notice, though, that the Welch test here, since the ends are not dramatically unequal for the two groups, they're unequal, but not dramatically so. You're getting essentially the same thing. Cohen's D is about the same. The T statistic is almost exactly the same. It's not making much of a difference. So again, it can make the biggest difference, and you really need that correction factor at times, or at least check for the correction factor if you have highly unequal ends. In terms of the normality distribution, you can use the Mann-Whitney U. And the Mann-Whitney U is a test, rank ordering test, where it gets rid of these huge differences where the distribution is really spread out. It basically reduces that by doing a rank ordering and gives you a significance test. But that too is coming out as highly significant. So any way you cut it, you have a significant difference between these groups. And I'll try to keep this video reasonably short, so I'll stop there. Thanks.